Assalamualaikum. Hi everyone. We are now in the fifth subsection of topic 3, and in this subsection we are going to see some relations between A and a subspace. Some subspaces of Rn. Recall that Rn here is the n-dimensional Euclidean vector space. And recall as well that n-dimensional Euclidean vector space is whenever we equip the space Rn with addition and scalar multiplication. Okay, so to get subspaces of Rn, we firstly have to compute some rows, some vectors from A. The vectors are row vectors and column vectors. First of all, we are going to see in this slide how to compute row vectors. As you can see from this equation, on our right hand side, we write A in terms of R1, R2 up to Rm. It's supposed to be Rm here. Where R1 is a row vector, the first row vector corresponds to the first row. Okay, so first row vector is row 1. And then we are going to have R2 correspond to the second row and up to M row. Up to M row here, where row vector Rm is correspondent to M row. So since the size of A is M times N, therefore we have M number of row vectors. Assalamualaikum. Hi everyone. We are now in the third subsection of topic 3, where in this subsection we are going to see some relations between A and subspaces of Rn. Recall that Rn is the Euclidean n-dimensional Euclidean vector space. Okay, and n-dimensional Euclidean vector space is Rn whenever we equip Rn with standard addition and scalar multiplication. Okay, so to have subspaces of Rn, we firstly have to compute some vectors from A. We are going to have row vectors and column vectors. Firstly, how to get row vectors? As you can see from this equation, the right hand side here is we write A in terms of R1, R2 up to Rn, where R1 is represent the first row. Okay, R1 represent the first row, and we denote the first row vector R1 as a vector where the entries of R1 we took it from the entries of the first row. And in total we are going to have M number of, so it's supposed to be M numbers of row vectors, because A is of size M times N, therefore we are going to have M number of row vectors. For the column vectors, we are going to have N number of column vectors, where the first column vector C1, okay, is from the first column, and we do the same up to N column vector Cn, where we get Cn from the N column of A. In this example, we are given a matrix of size 2 times 3, 2 rows and 3 columns, and we have to compute row and column vectors of this matrix. Okay, since the matrix has 2 rows, therefore here is the row vectors R1 and R2. R1 we took from, R1 is correspondent to the first row, and R2 is correspond to the second row. And we are going to have 3 column vectors where C1 is correspond to the first column, C2 correspond to the second column, and C3 is corresponding to the third column. So from the matrix of size 2 times 3, we are going to have 2 row vectors and 3 column vectors. Now we are going to introduce row space and column space, where they are subspaces of Rn and Rm. Subspaces of Rn and Rm. Row space is a subspace of Rn, and column space is a subspace of Rm. Okay, so we have a matrix of size m times n, and we have m number of row vectors here, and then the row space for A is a subspace of Rn, where the subspace is spanned by a row vectors of A. So we write this way: row space for A is a subspace of Rn, okay, where this space is spanned by all row vectors of A. Okay, recall what does it mean by row, what is mean by span. Okay, span, space spanned by these row vectors is a collections of all vectors that can be write in terms of can be write as a linear combinations of all row vectors R1 up to Rm. Okay, so this is a subspace of Rn because R1, R2 up to Rm are all vectors in Rn, right? Because all R1, R2 up to Rm, they are all vectors in Rn. Okay. Okay, the same goes to the vector space for A. Firstly, from A we get n number of column vectors, where all of these column vectors are in Rm. Okay, therefore we define vector space for A as a subspace of Rm, where this subspace is spanned by all column vectors C1 up to Cn. Okay, by the definition of span, that means the space is a collection of all linear combinations of C1, Cn up to Cn. We are given the matrix A as follows, and we are going to get it row space and column space for A. As defined earlier, row space for A is the following subspace of R3, where every element of the row space for A can be written as a linear combinations of all row vectors of A. The row vectors of A is first row vector, second row vector, and the third row vector. So X, Y, Z here is an element of row space for A, where X, Y, Z is a linear combinations of these 3 row vectors for A. Right, then we might ask, what's an example of vector in row space for A? Okay, can I get one example of vector in row space for A. Okay, from here, every element of this space is a linear combination of row vectors from A. Therefore, okay, one example is we consider A1 as, let's say, 1. We consider A2 as 2. And let's say this is A3. A3 as 0. So one example is minus 1, 3, 2 plus 2, 4, minus 6 plus 0, 0, 0. And we are going to have 1, 7, minus 4. So this is an example of vector in row space for A. Now we are going to get column space for the matrix A, which is given by this. Column space for A is a collection of all vectors from R3, okay, where the vectors, the vector in R3, x, y, z, where x, y, z can be written as a linear combinations of column vectors of A. Okay, as follows, where A1, A2, A3 are any real numbers. So we might ask again, what is an example of vector in the column space for A? Okay, to get one example, we might choose A1 as 0, A2 as 1, A3 as 1. Okay, so the example is x, y, z equal to x, y, z equal to 0, 0, 0 plus 3 to 1 plus 2 minus 3 minus 2, which is equal to 5 minus 1 and minus 1. So this vector is an example of vector in the column space for A. This theorem gives a relation between column space for A with a system of linear equation. This theorem says that we have a matrix A. And remember, AX equal to B is a systems of linear equation. Where its coefficient matrix is A. Okay, and this theorem says that if vector V is one of the element in the column space of A, then the systems of linear equation given by AX equal to B is consistent. Okay, you may look at the detail of proving that I have provided in the slide. Let's see an example of a matrix with its corresponding systems of linear equation to make sure that we understand Theorem 3.14. So we have a matrix. This is matrix A. This is matrix A, and the whole equation represents AX equal to B, a systems of linear equation with coefficient matrix A and vectors B as parameters for the systems of linear equations. So from the previous examples in the previous lectures, this systems of linear equation is consistent with this following solution. It has unique solution. and therefore the systems of linear equation is consistent. So the systems of linear equation with coefficient matrix A is consistent with the unique solution, and to verify that theorem we have to answer, is B in the column space of A. Okay. We want to check if the vector B is in the column space of A. So we have to look at the column space for A as given by this set. Okay, and okay, to check B, since B is a linear combination of column vectors of A, because of this, B is a linear combination of column vectors of A. Okay, therefore B is in the is in the column space for A, and we have verified the theorem by using this example of matrix and systems of linear equation. Okay, given a matrix A, we are going to compute two subspaces, column space and row space, where both are subspaces. Both spaces are subspaces of Rm and Rn respectively. Okay, therefore, since they are subspaces, then they are also vector spaces, and we know that every vector spaces must have basis. Every vector spaces must have basis. So this theorem helps us to get a basis for column and row vectors. However, to use this theorem, we need to make sure that the matrix is already in row echelon form. Okay, this theorem says that if R is a matrix which is in row echelon form, okay, so we have R in the row echelon form, and since it is in row echelon form, so we should be able to find the leading one. Okay, doesn't matter what it is, we have to find, we have to identify leading one for each column and each row of the matrix R. Okay, so from this leading one, we are going to identify basis for column space and row space. This theorem says that row vectors with the leading one form a basis for the row space. So any row vectors that consist a leading one form a basis for the row space. Bear in mind that in REF form, there might be a rows that doesn't have any leading one. Okay, and the same goes to the column spaces. Okay, again we identify column with leading one. The column with leading one forms the column with leading one will form a basis for column space. That's what's stated by this theorem. Given a matrix R that already in REF form, okay, with this leading one, okay, you have to determine a basis for row and column space of R. Okay, so this is row space, which is subset to R, sub 1, 2, 3, 4, 5, subset of R5. And as given by the theorem, the basis for this row space is a row vectors which consisting the leading one. Okay, therefore R1, R2, and R3. Okay, R1, R2, R3 are row vectors that consist the leading one. Therefore, R1, R2, R3 are the basis for this row space. R4 doesn't contain the leading one. That is why R4 is not one of the row vectors that form a basis for the row space. This is the row space. And by the theorem, these three row vectors form a basis for the row space because these row vectors consist the leading one. As for the column space, this is the column space where we have 5 column vectors in R3, if I'm not mistaken. We check that later on. And only C1, C2, C4 has leading one. So C1, C2, C4 are column vectors that form a basis for the column space. So these are 4. The previous theorem only tells us how to get basis for column space and row space for a matrix that already in row echelon form. So we might question how to get a basis for column space or row space whenever the matrix not in row echelon form. This theorem, theorem 3.16, at the second part might help us. It states that whenever A and B are row equivalents, A and B are row equivalent matrices, and it states that if we know basis for column vector for A, we also may compute basis for the column space for B. Okay, it states here that we look at the corresponding column. Okay, basis for column space for A, we look at the correspond row vectors in B, and that row vectors in B are going to form a basis for the column space for B. To understand this, we may look at the next example. Okay, so in this example, we have a matrix A that's not in the row echelon form, and we are going to get a basis for the column space of the matrix. So firstly, we are going to perform elementary row operations to reduce A into row echelon form. Let's say a matrix R. So the matrix R, which is a row echelon form of a matrix A, so A and R are row equivalents, and from the previous theorem, we may get a basis for the row space by firstly identify the leading one. Therefore, basis for column vector of R are column vectors C1, C2, and C3. And then to get basis for column vector for R, we look at the corresponding column in A. Okay, so we have column 1, 2, and 3 in R. Therefore, we have to consider column 1, 2, and 3 in A. Okay, column 1, 2, and 3. 2 and 3. And these column vectors form a basis for the column space for A. Basis for column space for A. The theorem 3.16 only states how to get basis for the column space for A whenever A not in row echelon form. So we might ask, how about basis for row space for A? We actually will able to use theorem 3.16 again for the second part of theorem 3.16 to get basis for row space of A by transpose A. We get a transpose of A. That means we converting the row space of A into the column space of A transpose. Okay, so we get A transpose. And then we find basis for column space of A transpose. And then this next step, the basis for column space of A transpose is actually basis for row space of A by transpose it again. Okay, so you may try this method to get basis for row space for this given matrix. The matrix A is, the matrix A here is the A here is A is 1 minus 2 0 0 3 2 minus 5 minus 3 6 0 5 15 10 0 and 2 6 18. Okay, so given the matrix A, try to get basis for the row space of A by using theorem 3.16 part 2. And you may find out that the basis for the row space is formed by R1, R2, and R4. We are going to introduce another space which is called null space for a matrix A. Null space for the matrix A is actually solution space of a homogeneous system of linear equation Ax equal to the 0 vector, which is a subspace of Rn. So, we are given a matrix A. Okay, A is a matrix of size m times n, and then from a matrix A, we are going to get a systems of linear equation, homogeneous systems of linear equation. Homogeneous system of linear equations is when the parameters here are all zeros. Okay, null space for A, null space of A is a solution space for the system of linear equation. We get the solution for the systems of linear equation. It forms a space of subset of Rn, and the space is called null space for A. Okay, so null space for A is given by follows, where it is a collection of all x in Rn, where x satisfy Ax equal to 0. Okay, so x satisfy Ax equal to 0. That means this x is a solution for systems of linear equation Ax equal to 0, which is homogeneous systems of linear equation with a coefficient matrix A. Okay, in this example, we are given a matrix A of size 3 times, of size 4 times 5. Okay, so we are asked to get a null space of the matrix A. And we know that the null space for A is the solution space for the homogeneous systems of linear equation with coefficient matrix A. Homogeneous systems of linear equation with matrix A means that it is Ax equal to the 0 vector. Solution space, that means this is a subset of R5. These four equations form a homogeneous systems of linear equation for coefficient matrix A. Okay, and we have seen in example 3.32 that the solution for the systems of linear equation is given by this equation. Okay, where it has two free parameters s and t, and we are able to write the solution in terms of s and t, which is equal to s. Okay, look here how to get this. S, the coefficient for s is -1. That's why we get -1 here. In the second row, the coefficient of s is 1. So that's why we have 1. The coefficients for s here is, in the third row, is 0. So that's why we have 0. The same goes to the fourth row, we have 0. And the same goes to the fifth row, since there is no s. So the coefficient for s is also 0. And then for t, okay, we are going to look at the coefficients for t at each row. The first row coefficient for t is -1. In the second row, it's 0. The third row is -1. Fourth row, it's 0. And the last row, fifth row, is 1. Okay, so this is the solution space for the systems of linear equation Ax equal to 0 vector, and therefore this is the null space for A. Null space for the matrix A. Why does the null space of A is given by this set? That is because, okay, from the previous slide, we have systems of linear equation as follows, and the solution for the systems of linear equation solution of ax equal to 0 is given by x1, x2, x3, x4, x5, okay, is given by s minus 1, 1, 0, 0, 0 plus t minus 1, 0, minus 1, 0, 1. So the solution for ax equal to 0 is given by this. And we know that null space of A is a solution, is a set of solution of the systems of linear equation ax equal to 0. That is why the null space of A is any vectors in R5 such that the vector can be write as a linear combinations of this and this. So that's why we have this set as a null space of A. Okay, and then a basis for the null space. Okay, you may check that these two vectors v1 and v2, they are linear independent, and from this we can see that every element, every vectors in the null space can be written as a linear combinations of v1 and v2. Therefore, v1 and v2 form a basis for the null space of A. In this example, we are going to see relation between general solution of a systems of linear equation with null space. Okay, so we have systems of linear equation, and refer to the example 1.12, we have this solution. Again, since the solution of the systems of linear equation has three free variables, remember R, S, and T are R, S, and T are parameters that makes solution of the systems of linear equation have three free variables. And therefore, we write the solutions of the systems of linear equation in terms of R, S, and T as follows. Okay, and we have one part in the red vectors here where it doesn't depends on R, S, and T. Doesn't depends on R, S, and T. And this part is called a particular solution. Particular solution for Ax equal to B. That means whenever R equal to S equal to T equal to 0. Okay, so whenever R, S, and T is equal to 0, we have this solution, and we call it as a particular solution for Ax equal to B. And the other parts of the solution in the green font, it's form another solution that we call as the general solution for Ax equal to 0. That means the green part is the null space for A. Okay, because the green part is the general solution for Ax equal to 0 vector. In the previous slide, we have seen the relation between a solution for Ax equal to B with null space. This theorem states the general statement for the relation between a systems of linear equation Ax equal to B with the null space. It says here that, okay, we have x naught as any solution of consistent systems of linear equations Ax equal to B, and we have a basis for the null space of A, where the basis is given by vectors in the set S, and therefore every solutions of the systems of linear equation can be written as this, can be written as x naught plus plus the, okay, if you can see, x naught plus the green part. The green part is a linear combination of vectors in the basis. Therefore, the green part is the element in the null space. So this is the element of vectors in the null space. Okay, the converse is also true. Please reread this theorem and try to understand. Let us start by understanding this question first. After that, we are going to figure out how to solve this. Right, so we have Euclidean vector space R4. And then we have 6 vectors from R4. We have V1, V2, V3, V4, V5, and V6. From these 6 vectors, this vectors is going to form a subspace. A subspace V, where V is given by span V1, V2, V3, V4, V5, and V6. Okay, so this space is a subspace of R4, where this space is a subspace that's spanned by V1 up to V6. In this example, the question wants us to find a basis for this subspace. Okay, now we are going to relate this question to the methods of getting a basis for a column space for a matrix. Okay, so we are going to use that method to answer this question. All right. So firstly, we are going to form a matrix. Okay, so V1, V2, V3, V4, V5, and V6 become a column vectors for a matrix A. So we have a matrix A here, where the vectors V1 up to V6 are column vectors for A. And after that, in the next slide, to get basis for the column space for the matrix A, we have to reduce the matrix A to REF form as follows. Okay, from this REF matrix, which is a row equivalent to the matrix A, we found that it has three leading one, 1, 2, and 3, where these leading ones are in column 1, column 3, and column 5. Therefore, from theorem 3.15, we conclude that basis for the column space for the matrix A is vector 1, vector 3, and vector 5. And therefore, these three vectors form a basis for a subspace for R4, which spanned by the previous 6 vectors. And that's the end of this subsection. Thank you. We are now in the last subsection of topic 3, and we are going to discuss on rank and nullity of a matrix. This lemma discusses on dimension of a row space and column space for a matrix A, where it says that the dimension of row space and column space are both similar for a specific matrix. To understand this, we may recall that whenever we are given a matrix A, whenever we are given a matrix A, we are able to derive row space and column space for the matrix A. And if you recall, row space is a subspace of Rn, and column space is a subspace of Rm. Whenever A is of size, is a matrix of size M times N. And since a row space as well as column space, they are both subspaces, therefore they are vector spaces. They are vector spaces. And we know also for every vector spaces, there are bases that represent the vector space. So again, in the previous subsection, we have seen how to determine. We may determine basis for this vector space, for vector space. And basis is not unique. For a specific vector space, basis is not unique, but the number of vectors in the basis must be similar for a specific vector space. And recall as well that the dimension of a vector space is given by the number of elements or the number of vectors in basis. Okay, and we may recall as well that whenever we have a matrix A, to get a basis, for A, we perform ERO, elementary row operations, to get a matrix, row equivalent matrix in the form of reduced echelon form. To get a basis, what we did was we identify leading one. Okay, we identify leading one. Bear in mind that not every column has leading one. So we have to identify column and basis that consist leading one, and the correspond row or column which has the leading one form a basis for the column and row space. Therefore, the number of leading ones for REF matrix is similar to the number of bases for column space and row space. And that is why we may see that row space and column space have similar dimension. So now here come the term rank of A and nullity of A, where rank of A is defined to be the dimension of the row space as well as the dimension of the column space of a space A. And the nullity of A is the dimension of the null space of a matrix A. In this example, we are given a matrix A and we have to determine the rank and the nullity of the matrix A. Okay, so we know that the rank of A is the dimension of the matrix A, which means we need to determine the number of vectors in the basis for the column space or row space of A. Therefore, to determine the basis for column space or row space, we have to reduce A to row echelon form, let's say matrix R. Okay, and here is the reduced echelon form of the matrix A. We denote as a matrix R, and we know that R and A now is row equivalence. And from here we can see that R has two leading one. R has two leading one. Therefore, okay, there are two rows or there are two columns with the leading one. Therefore, the rows that has the leading one form a basis for the column or row space of A. Therefore, the rank of A is 2. That means the dimension of the column space or row space is 2. For nullity, we need to determine a basis for the null space of a matrix A. And recall that null space of a matrix A is the solution space for the systems of linear equation Ax equal to 0 vector. Okay, and here is the solution for the systems of linear equation Ax equal to the 0 vector. And from here we see that these four vectors form a basis for this solution space. Therefore, the number of bases for the null space is 4, and therefore the nullity for the matrix A is 4. Let us discuss on nullity again. Recall that nullity is equal to the number of element, number of vectors in basis for null space. That is why we need to determine basis for the null space of A. And recall that, what does it mean by null space? Null space is a solution space for Ax equal to 0. That is why we have to compute the solution for Ax equal to 0. And we found that the solution for Ax equal to 0 is given by this, where we may see here that we have 1, 2, 3, 4 parameters. There are 4 parameters here. And if you can recall, how do we determine a number of parameters that a solution of a systems of linear equation has? If you can recall, free variable correspond to 1 parameter. If you can recall, in the previous previous topics, we see that the number of parameters is equal to the number of free variable whenever we reduce the matrix into augmented matrix into REF form or REF form. So we may conclude that the number of bases for null space is equal to the number of free variable that the system may have. Okay, so this is equal to free variable. We are going to use this later on. Okay, this lemma says that rank of A is equal to rank of A transpose. That makes sense. We may see this quite directly because rank is the dimension of row space of A, and we know that row space of A, the dimension of row space of A is equal to the dimension of column space of A, and we know that the difference between A and A transpose, that they alternate column and row. Because of that, rank of A is equal to rank of A transpose. This example of matrix A verify that theorem. You may compute A and A transpose and get rank for these two matrices, and you may found that rank of A and A transpose is equal to 2. This theorem is very important because it helps us to determine rank of A or nullity of A by using the number of columns of the matrix. It says that if A has n number of columns, n, therefore n is equal to rank of A plus nullity of A. The proof of this theorem, because we know that, you may recall that rank A is equal to the number of leading one in RREF form of A, and nullity of A, as we have just discussed earlier, is a number of parameter for solution for systems of linear equation AX equal to 0 vector. And recall that number of leading one is equal to number of leading variables. Number of leading variables, and number of parameters is equal to the number of free variables. That is why the number of columns is a summation of number of leading variable and the number of free variables. For example, the matrix A has six number of columns. This matrix A has 6 number of columns, and rank of A is 2, and nullity of A is equal to 4, where 6 is equal to 2 plus 4. Our final theorem in this topic. This theorem gives 4 statements which are all equivalent to each other. For these statements, we have to consider A be a matrix with n columns, and the first statement says that rank of A is equal to n. Rank of A is equal to n, that means the number of leading one is n. The number of leading one is n, and the number of leading one is equal to the number of column. That means whenever we have AX equal to B, a system of linear equation, remember that one of the methods to solve this systems of linear equation is by get the augmented matrix, of the systems of linear equation, and then to solve this by using Gauss-Jordan elimination, we reduce A to RREF. Gauss-Jordan elimination, we reduce A into RREF form, and since the number of leading one is equal to the number of columns for the matrix A, that means every column has a leading one. Every column has a leading one. Remember that one column corresponds to one variable. So here, whenever every column has a leading one, therefore every variable have a leading one. Therefore, every variable has a solution, unique solution. That is why we have statement 2, where AX equal to B has a unique solution. For a column, the third statement says that column vector for A span Rn. That means Rn is equal to the span C1, C2 up to Cn, where the vector C1, C2 up to Cn are column vectors for the matrix A. And this means that every x in Rn, x is a linear combination of C1 up to Cn. Therefore, K1 C1 plus K2 C2 plus up to Kn Cn. That means the scalars K1, K2 up to Kn exist such that x is equal to this summation. Okay, and in the fourth statement, it says that there exists a matrix B such that AB is equal to the identity matrix of size n. If A is a square matrix, then this is quite obvious. If A is a square matrix, for the case A is square matrix, then remember that the method to get the inverse for A is we have to perform E row to replace A into the identity. Since A has leading 1, since every column has a leading 1, that means we are going to get the inverse of A, and for square matrix A, B is the inverse of A. And that is the end of topic 3. Thank you.